Today we're happy to have Obied from Oxford. He'll tell us about universal bounds on brane synthesis.
Okay, thank you so much, and thank you all for having me here. It's been a fun couple of days, these past 2 days, and I will be here until the end of next week. So if anybody has anything you want to discuss related to maybe pheno of this or any other thing, please come to my office. I'm sitting upstairs in 345. Okay, thank you so much. So today I will present a bound on branes and the sitter. So actually 2 of them, depending on which brane we're talking about. And this is work that is to appear soon with John Marsh Russell and his student Saqib Hassan, both of which are at Oxford. So let me start. This one. You probably have to click on the presentation again. Zoom. Oh, it's good. Okay, so let me start with some motivation. So we've known for some time now that quantum gravity can have qualitatively different features, whether we're talking about ADS, Minkowski, or de Sitter, and there are several examples of this. One can think, for instance, about holography, which is very natural and easy to formulate in ADS, but that's not the same cannot be said of de Sitter or Minkowski. Also, for instance, black hole solutions can be different in ADS, de Sitter, and Minkowski. In ADS, for instance, the thermodynamics of large black holes are different from the thermodynamics of large black holes in Minkowski. In ADS, they don't evaporate. Okay, so there could be several qualitative differences in gravity, whether we live in Minkowski ADS or the Sitter space. And so it's important to of course understand all of them. But in the case of de Sitter, we believe that we live in a universe that is close to de Sitter. And so results about quantum gravity in de Sitter are particularly appealing because they could apply to our universe early or now. However, these results are difficult to come by from top-down approaches because of difficulties with de Sitter constructions. So even with the full power of string theory, it's sometimes difficult to make very sharp and precise statements. The strongest methods we then have are bottom-up arguments as to why certain things should be true in de Sitter, and so these are the one of the most robust handles we have on quantum gravity in de Sitter. And today I will talk about one such bottom-up argument. In particular, we're going to use black hole physics in de Sitter space, and I'm going to argue for why the tension of branes in de Sitter space cannot be too small. So it should be bounded below by some number, and we will see more details of this later. Of course, it goes without saying, if you have any questions, stop me at any time, and we can. Yeah. Okay. So one such example of a bottom-up argument is in de Sitter is the Festina-Lente bound, and this was introduced in this paper in 2019. I will say a lot more about this, so I will actually go through the argument in detail during the talk. But just for now, I'm just trying to give a big picture. So Festina-Lente in Latin means to hurry slowly, and the phrase refers to the evaporation of certain large charged black holes in de Sitter space. Okay, so de Sitter space has a cosmic horizon, which is not there in Minkowski space, and so there is a notion of a largest black hole that can fit in de Sitter space. Okay, so this notion is absent in asymptotically flat space. So these largest black holes are on the verge of becoming super extremal. So this is like a sort of extremality bound, which is similar to the extremality bound of rest and Nordstrom black holes. But in this one, it is the Sitter horizon and the outer black hole horizon that are involved, rather than the inner black hole horizon and the outer black hole horizon. Okay, so if we consider one of these really big, so the biggest black holes that can fit in de Sitter, and we consider a charged one of those, these black holes, like I mentioned, are on the verge of becoming super extremal, so that they're on the verge of violating an extremality bound.
So the naked singularity only happens in de Sitter?
The naked, well, these black holes I'm talking, so there could be naked singularities in asymptotically flat space, but these big black holes I'm talking about are only in the sitter.
This bound only applies in desitter.
Yes, this bound will only apply in the sitter, yes. Okay, so if we consider one of these really big black holes and consider a charged version of it, so the cousin of the Rice-Nordstrom black hole in asymptotic flat space, and if we have a theory which has light charged particles, then these charged particles can screen the electric charge of this black hole very quickly. And we can see that by evolving the equations of motion, you can see that this black hole will be pushed beyond that extremality condition. Okay, and so it will develop. So the space-time will develop a naked singularity, which, if you believe in cosmic censorship, should not be should be forbidden. Okay, so to avoid this fate, we must ensure that the theory does not have these sufficiently light particles. Okay, so the theory should not have these light particles, and the condition that we get is that m squared, which is the mass of the particle, is bigger than its charge, which is g times q, times m Planck, which is the Planck mass, and h is the Hubble rate, and in the sitter it's related to the. I'm just defining h to be square root.
Isn't the existence of desitter space against some other sacred rules?
Well, okay, yeah. So here I'm not. Yes. So the existence could be against some other rules. Here I will not discuss. This is bottom up, so I will not discuss any existence or non-existence of the sitter from top-down construction.
But those are also bottom up, I thought.
No, I mean they're motivated by string theory. So this one here, I'm assuming the sitter exists for this talk. I'll assume the sitter exists,
Okay.
and then I will derive a bound. And if it doesn't exist, then my bound will apply trivially because the premise doesn't exist. But if it exists, then this bound applies.
What is the time scale for it to evolve to this naked singularity?
The time scale is m Planck Hubble, so it's set by m Planck Hubble. Rather than, yeah.
What is this bound in the real world?
This bound says that the masses of charged particles should be higher than milli-electron volt.
I think real world, I just checked, but I think electron satisfies this part.
Yes, electrons satisfied. So the only one which is on the verge of this bound is the neutrino, but the neutrino is not charged, and so the right-hand side here has 0, and so it's also fine. So
What is G?
G is the gauge coupling. So this is the charge of this is a charged particle. This is bound on mass of a charged particle, and G is the gauge coupling of the U1 under which this particle is charged. So I'll give more details about this in a few minutes, but just to set the picture. Okay. And so Hubble here is the Hubble rate, like I said, and lambda is the cosmological constant, and so this is quoted in 4D. All right. So this bound, like we saw, has a relationship to black holes not becoming super extremal, and so it's really in the same spirit as.
Sorry, just for me,
Yeah,
I'm not the expert on this.
Yeah.
What's wrong with the naked singularity?
Yeah. So like I said, we believe that reasonable initial conditions and reasonable generic initial conditions should not evolve into naked singularities by cosmic censorship. So it's a conjecture to cosmic censorship is but we don't know exactly.
So I'm supposed to believe in cosmic censorship?
Yeah, so this is derived from cosmic censorship. So if cosmic censorship is.
What's wrong if that's violated?
If cosmic censorship is what? Well, I mean, then I guess you have to give initial conditions. So this is Benro's old argument, which is that you have to know what happens at the singularity, and that's like very UV physics. And the expectation is that GR as a low energy effective field theory should make sense without knowledge of this very UV physics. So that was his original argument as to why it should be censored. Yeah, because if you have a naked singularity, then you will have to know what happens at regions of very high curvature, and that's UV physics. So you have to impose some boundary condition there. So Penrose thought that was unnatural, and so he said that all singularities should be closed by horizons. So we don't have to know about UV physics for GR to make sense.
That argument by itself is probably, I mean, at least in field theory, we wouldn't take that seriously. We have certainly situations where there are defects in the theory, and if you look at very short distances, it's resolved to something smooth in some UV theory.
Right. Yeah, that's true. Yeah, for instance, in string theory, so there are examples where these things are cloaked by others. Yeah, that's true. But again, so this is just if you throw away cosmic censorship, then I have nothing to say. But so this is assuming cosmic censorship. which is reasonable. I think, I mean, it's not, yeah.
So to summarize, your assumptions are cosmic censorship, existence of de Sitter, and Hawking radiation.
Yes, Hawking, in this case, it will be, yes, of charged particles, but then I will discuss more about the assumptions in a bit.
Okay.
Yeah, so I will review this paper in some detail in a bit. So this is just still the motivation. Okay? Yeah, I will say a bit more about this. Okay, so this bound has something to do with you know, with black holes being super extremal, and somehow has a spirit that is similar to the weak gravity conjecture. And the weak gravity conjecture is related to the evaporation of extremal black holes, but in asymptotically flat space. Okay, so extremal black holes have Q equals m, and if or you can consider a near extremal black hole if you want to be pedantic with Q very small to m. And so if you consider that black hole and you ask, can that black hole evaporate? Then the kinematic condition that you find for that black hole to be able to lose charge is that there should exist a particle whose mass is lower than its charge. Okay, and so these things show up always in string theory. We always, in all models, we have particles whose mass is less than its charge. In our universe, and the electron is an example of this. And so this is called the weak gravity conjecture because for this particle, gravity is the weakest force. So the repulsion, the electrostatic repulsion, is stronger than the gravitational attraction for two instances of this particle. Now, the weak gravity conjecture also has a natural generalization to extended objects that are branes. And for example, one can look in this paper, and it requires that there are branes that exist whose tension is low enough in Planck units compared to the charge. Okay, and so a very natural question is there an analog of this statement for branes, but for the Festina-Lente statement? Okay, so these two are similar. Festina-Lente and weak gravity are similar. They're both statements about the evolution of extremal black holes. And the weak gravity conjecture has a particle version and a brane version. Festina-Lente so far does not have a brane version. And so you can ask, is there a brane version of the Festina-Lente conjecture?
Are you asking the question within string theory or for any theory of quantum gravity?
For any. So the Festina-Lente one will be for any. It's bottom up.
Okay.
So I will,
and also your question about extending it to branes.
yes, so that will be bottom up. The brane extension will be bottom up. Yeah. So for any theory, it should apply. Whatever I say, yeah. Okay. So any questions about the motivation? Okay. All right. So with that motivation in mind, this will be the outline of the talk. So I'll start first with some somewhat in-depth review of this Festina-Lente bound, because what I say will be similar in spirit to this. And then I will talk about how one can get a Festina-Lente bound that says things about branes. In this part, I will comment about how the branes of string theory satisfy this bound, and I will also make a comment about axion domain walls. So this could be very interesting for phenomenology, but yeah, I will tell you more about it later. So and then I will summarize and provide some future directions. So the first part is just based on this paper. Okay, so let's now look a bit more in depth at the Festina-Lente bound. And the big picture, like I said, is we want to consider these large charged black holes in de Sitter, and we want to avoid any pathological evolution. And by pathological, I mean evolution that would lead to naked singularities. Okay. So the setup is very simple. We start with Einstein-Maxwell theory in de Sitter space, and we add charged matter of mass m. Okay, so there's the Ritchie scalar and the cosmological constant lambda, which we had seen before, and then there is a U1 field, a U1 Maxwell field, whose field strength is F. So if we ignore this part for now, if we ignore the charged matter, then this theory has black hole solutions And they are labeled by two numbers. Their mass, we're gonna call mass M, and their charge Q. Okay, so these are the usual, the usual cousins of the Reissler-Nordstrom solutions in asymptotically flat space. And just like the Reissler-Nordstrom black holes of flat space, we would expect that reasonable solutions satisfy certain conditions. For example, in flat space, there's an extremality bound that requires that the charge of these Reissler-Nordstrom black holes is smaller than M. And in the sitter, it should not be any different. After all, if this black hole is very small, it should feel like as though it is in flat space. Okay, and so you expect some bound that says that Q is less than M, and so things above this line are somehow bad. Not bad, but they have naked singularities. Okay, so there's solutions that, so there's solutions that we don't believe are physical, if by cosmic censorship. But in the sitter, there's another thing that happens. So like I said, the sitter has a horizon, and so there's a notion of the largest black hole. So if you start with a small black hole in the sitter and you increase its mass, the black hole will get bigger and bigger, and at some point it won't fit inside the sitter anymore. And this notion is absent in asymptotically flat space. Okay, so you would imagine that black hole masses are bounded above by some, by some number m max, and so there's a vertical line here, and the region towards the right of this vertical line are not good black hole solutions either. Okay. So we can do this calculation more carefully, and indeed, the intuition that we had from flat space and knowing that the sitter has a horizon works out exactly correctly, and the region of sub-extremal black holes lives inside the shark fin. So things inside here are good, and the things outside here they have naked singularities. Okay, so this is the space of black hole solutions in the sitter. It's the thing inside this shark fin region. Okay, so let me make a few comments about this. This upper branch of solutions are the extremal black holes that we know. For example, here they look like the extremal black holes of asymptotically flat space. And their near horizon region is ADS2 times S2, which is the one that we usually know. So for extremal black holes, if you go near the horizon, then space-time would look like this. Okay. And this branch is the branch. So the weak gravity conjecture is actually a statement about this branch. So things here should be able to decay. And so if you want to decay, you want to lose some charge. And so you have to have a particle whose charge is large enough compared to its mass. Okay, so if you are on this branch and you want to decay, you want to go down, you don't want to go to the left. And so the weak gravity conjecture is exactly a statement about this branch. But in the sitter, we have a different branch, and so you can ask a similar question. Okay, so in the sitter, there's this other set of solutions that are also, almost super extremal. And so you can ask a similar question: if there's a black hole here, how do I ensure that it decays nicely? We don't want it to go outside the shark fin region. We want it to go inside. Okay. So in the sitter, these are the largest black holes, and they're called Narrow black holes. And their geometry, just like this is ADS2 times S2, their geometry is DS2 times S2. Okay, any questions about this?
What is M max in the real world?
M max in the real world? Oh, so it's set by, it's set by Hubble. It's a black hole that's the size of the universe, and so it's very large. I don't know. Yeah. Yeah, it's set by Hubble, so it's a black hole that's the size of the universe. Yeah.
What's wrong with black hole bigger than the size of?
Yeah. So what's wrong is that they are outside this this region, and so they have naked singularities. So those space-times have naked singularities.
If the horizon is bigger than the sitter horizon.
Yeah, if the black hole horizon is big, right? So whenever we have two horizons, if they cross, then
There's a naked similarity.
then you typically get naked singularities. Yeah. And so here, if the black hole horizon somehow crosses for these, if you make it bigger and bigger, then you'll get naked singularities.
This is a time-like singularity?
Yes.
But mechanically, if I just make things, you just say it's just impossible to build such a black hole.
Yes,
Bigger
it's
and
it's
bigger.
very hard, right? It's very hard to, yes, of course, it's very hard to build, although in eternal de Sitter, these will just be nucleated from the horizon spontaneously. So if you wait long enough, then the horizon will have a fluctuation that gives you one of these big black holes. So they just spontaneously. So if you just wait, you'll have to wait a long time, but
The payment is impossible to make a bigger one.
oh, yes, it's impossible to make a bigger one by construction, you mean?
Yeah.
If you try to construct it?
Yeah.
Yeah, I don't think you can.
Obstruction is
Right, so I think, so, I mean, you would need to collect enough mass, and in order to have a black hole that's the size of the universe. I think, if you have a limited, right, so I think with reasonable evolution and if you have a limited access to space, I don't think that's possible. Yeah. All right. Okay, so these black holes, if we start with one of these black hole solutions, the good ones inside the shark fin, then these black holes will lose mass by emitting gravitons, so they can, by emitting gravitons, photons, or any other uncharged particle, and that will take them to the left in this figure. And they can also lose charge by emitting charged particles, and that will take them down in this figure. Okay, and the process by which they lose charge, you can think of it as Schwinger pair production, as was outlined in these papers, for instance. Okay, so Schwinger pair production, if you have an electric field, that electric field can Schwinger pair produce, and so these produced particles will screen the electric field, and this is one way that this black hole will lose charge. Okay, so for the rest of this talk, we'll only focus on this Naria branch, so we'll only talk about these spacetimes. Okay, so in these spacetimes, like I said, spacetime is de Sitter 2 times S2, and so it looks something like this. So here I'm showing de Sitter 2, so this is the one spatial direction of de Sitter 2, and there's a time direction that we're not drawing, and then the vertical direction here represents the S2. So there's an S2 orthogonal to de Sitter 2. Okay, and in this limit, there are two horizons. There's the black hole horizon, and then there's the cosmological horizon, and there's a constant electric field that runs between them. Okay, so the space-time just looks like this. It looks like almost like a parallel plate capacitor with negative and with positive and negative plates. And the magnitude of this electric field is m Planck Hubble. Okay, so it's a constant electric field between two with magnitude m Planck Hubble. So like I said, so what can happen is that this electric field can be discharged by producing E plus E minus, for example, or other charged particles. And the rate is set by the Schwinger rate. Okay, so the Schwinger pair production rate is proportional to m squared over GQE. This is in the exponential. There's a prefactor here that's set by the electric field only. It doesn't depend on the mass of the particle. And this prefactor, because it's set by the electric field, is large. It's m Planck h. Okay, for an area solution, E, like I said, is m Planck h, so you just substitute for E here. And then you can consider two important limits. One limit in which this process is exponentially suppressed, so m squared is much bigger than gm Planck h. And there's another limit where m squared is smaller than, much smaller than gm Planck h.
Is that formula reliable in the second limit?
Sorry, in this limit? Yeah.
That's like a strong coupling.
Well, I see. So I guess what happens is that you can imagine dialing the mass down, and the rate keeps getting faster and faster. And so it would be very weird if the rate just somehow stopped getting faster at some point. I mean, we don't have to take this limit, but you can take.
I'm just asking about the assumptions that when the calculation that produced that exponent.
Right.
That's
So
it's a weakly coupled calculation. That's why it's exponentially suppressed.
yes, that's correct. So what you need to do is I guess physically, if you keep dialing the mass down, you'd imagine the process to become faster and faster. And this should tell you when the process is really fast. So the exponent would tell you when the process is really fast. It's true, maybe we need to do a different calculation, but the parametrics will be the same. Because it should link smoothly to the exponentially suppressed process. Okay. All right. Okay, so in the first limit, The black hole loses charge slowly, so something like this happens. So every once in a while, you nucleate a pair of these things, and then one of them falls into the black hole, the other one goes outside the horizon, and the electric field is slightly smaller. And all this is fine because if the black hole loses charge slowly, then it can lose mass, slightly more quickly, and then not go outside the shark fin region. But in this limit, this electric field can discharge very, very quickly. And so, and so if this happens, then I guess I'll show you on the next. So I'll show you on the next slide. Then the black hole can leave this shark fin region. So if this happens, we discharge the electric field, I guess, almost instantaneously compared to Hubble. So the time scale, the relevant time scale is Hubble, and this discharges on a time scale that's M-Planck Hubble. And so the time scale for this discharge is very, very fast compared to Hubble. Okay, so the time scale for this discharge is set only by the electric field in the limit where the particle is massless, and that is M-Planck Hubble. The electric field is M-Planck Hubble. Okay, so if this happens, so we can start in this limit. You can start with a black hole here, and we can write the equations of motion for the sitter 2 times S2, and evolve these equations of motion, and then you'll see that this spacetime evolves into a big crunch spacetime. Okay, so the interpretation of this of this evolution is that the whole spacetime somehow has fallen inside the black hole, and so the black hole is larger than what it's supposed to be, and black holes that are larger than what they're supposed to be are to the right of this line. Okay. So to avoid this kind of pathological evolution, you should require that the particles are massive enough so that the Schwinger pair production rate is not too fast. And so the reason I showed you, so in the paper they do a more careful calculation with this. So here we're using the flat space limit, but in the paper they calculate this more carefully, even in the sitter, etc. But really everything is set by this exponent. So at the end of the day, this exponent is the thing that will play the most important role, and this exponent is there in the flat space formula, and so I'm showing you just the flat space formula. Okay. Any questions about this? This is basically the main,
But black hole can have other ways of losing mass. They can evaporate the photons, evaporate the gravitons, and those are never important here.
Yes. So that's correct. But so that happens on Hubble timescales. This is much faster than that. So this happens first. So in other words, the black hole will lose some mass to photons and gravitons, but it won't lose enough to save it from this process.
So is this a sharp boundary? This is
No, it's not a sharp.
you are creating much greater and much smaller. Or what about the twice as big? Or,
Yeah. Yeah, it's not a sharp boundary. That's why there's this tilde here. So there's an order 1 number that
in principle, there's a computation you can do, right? Just
yes, exactly. So yeah, so I'm doing this with a master student at Oxford, but we're not done yet. But yes, there's a computation you can do which will determine this number.
I do understand the first part of the answer to Liam's question. Why don't other decay channels matter? Other ways of losing mass? Is it the competition?
Yeah, no, I guess you can lose mass, but then what you need to do I guess you need to make up the time scale from Hubble to M-Planck Hubble. The M-Planck Hubble is much, much higher. So you need a very, very large number of, for example, if you have a very, very large number of massless particles, that might save you. But you need a very large number in the hierarchy that is M-Planck over Hubble. And so so I guess so that's a loophole. If you have a very, very large number of massless uncharged particles, it might save you. But but that's not something, right?
What is the temperature of these black holes?
Oh, it's Hubble.
So it's really low.
Yeah, it's really, yeah. The temperature is Hubble. The Hawking radiation process is set by Hubble, but this process is set by M-Planck Hubble. And so this is faster. Other questions?
So the temperature of the black hole is set by Hubble? you said?
Yeah, temperature of black holes. Okay, good. Okay, so then there's a bound like this, so that particles are massive enough so that this process does not happen. All right, so that's the story with the original Festina-Lente bound. So now let me tell you a similar story about the the decay of these large sharp black holes, but in the presence of low tension branes. Okay, and the big picture is the same as before. We just want to look at these narrowly charged black holes in the presence of these low tension branes, and we can ask, can these low tension branes screen the electric field fast enough so that we can get the same pathology? If you want to avoid that pathology, then the brain tension cannot be too low. All right, so like I mentioned previously, I'll talk about two such bounds, and the two bounds depends on the coupling on how we assume the brain couples to the gauge fields. Okay, so the branes will couple to the gauge fields, and then yeah, so depending on which coupling they have, then we'll get slightly different bounds. So let's start first with the two branes. So we're working 4D. I will mention the general D result later, but we're working 4D now. So let's start with the two brane, whose action is something like this. So the first term is the tension, is the contribution from the tension of the brain. The second term is a coupling of the form A wedge F brane. So A here is a bulk gauge field, and F brane is the field strength of a gauge field that's localized on the brain. So these couplings are present in string theory, for example. And then this F brane also has a kinetic term that lives on the brain. Okay. So if you have a background A, like I mentioned, so A is a gauge field in the bulk, and its field strength is F. And if there's a background value for F in the bulk, then you could potentially think about nucleating these branes that would screen this F.
By bulk, you mean on the brain?
No, by bulk, I mean not on the brain. So FBR is on the brain, but these ones are in the bulk. Yeah.
So what about branes that only couple gravitationally? You have nothing to say about them?
Yeah, no, exactly. So just like Festina-Lente, they have to couple to the electromagnetism so that we can, right? So Festina-Lente has nothing to say about uncharged particles, for example. Okay. So in the presence of a profile for this FB of F brane, this can have a charge under the bulk gauge field A. Okay, so if F brane is non-trivial on the I guess on the brane wall volume, then this brane will have a charge under the bulk gauge field A. And so you can imagine nucleating one of these branes with one of these profiles and having it screen A. So having it screen the electric field in the bulk. And just like I told you before, this nucleation happens locally. So in the Festina-Lente case, the reason we're able to use the flat space result is because this nucleation of particles happens locally, and so the flat space production rate really, it captures the important physics. So here we'll also, just talk about the flat space rate for now, but it's possible to generalize this to this other production in curved spacetime. Okay. So, like I mentioned on the previous slide, we want to consider the production of the nucleation of these branes. And so we start with the usual de Sitter 2 times S2, which has an electric field between the black hole horizon and the cosmological horizon. And we want to think about the nucleation of a brane here. And so let's say the brane nucleates in some shape like this. That's spherical or close to spherical. And for this brane to have an electric charge, it must have a non-trivial F brane profile on it. Okay, so you can find the equations of motion of F brane and solve these equations of motion. And you'll find a profile where so I guess we need to solve these equations of motion in the presence of a background electric field. And then you can find a profile here on the brane where A phi, so the gauge field on the brane pointing in the phi direction, is non-zero. And so the relevant components will be the magnetic fields like F theta phi and it will be negative on one side and positive on the other side. Okay, so with this profile for F brane, this, for example, this sphere or spheroid will have a positive charge on one side and a negative charge on the other side. And so it can screen the electric field inside because it has charges. Okay. Once this is nucleated, it will expand. So just like in Schwinger pair production, once you nucleate an electron-positron pair, they are torn apart by the electric field. And here, once this is nucleated, it will again expand, and it will eat up the electric field, present in the region between these two horizons. Okay. So if we so I guess parametrically, if we solve for this F brane, we will get alpha times r cubed times e. So the field strength on the brane is proportional to alpha, which was the coupling. It's proportional to the bulk electric field E, and then dimensions will tell you the remaining dependence. And R here is basically the size of this nucleated brane.
Could you show the previous slide for a minute?
Yeah, of course.
So this violates parity. Coupling. You have a Chern-Simons like term, coupling A to F.
Coupling A. I mean, it could violate. Well, these things are present in string theory, right? So we could have them. I think.
Are they? Like if I take a D2 brane, yes, there are gauge fields on the world brane, but I'm not sure they couple to space-time U1 gauge fields like this.
So they are. They can be coupled to the other forms like CP minus one or something like that. They are. So there are terms of
coupling.
yeah. There's a CP. So there's a CP wedge e to the 2 pi alpha prime f minus p, and that will give you this kind of coupling. Like the Chern-Simons terms on the different string theory, they have this.
D4 brains have also A
Yeah.
and F.
No, but D2s should have it right.
Yeah,
D4 even.
C1 wedge, E3.
Yeah.
Yeah.
Minus B.
C1 brane.
C1 being
Yeah.
Paul Kumon, one full potential.
Okay, but I guess so this is because 2B is not parity invariant. You can have these couplings.
Those are 2A. Those are already 2.
2A.
D2, just for D2s. Yeah, okay.
2A is parity invariant. Really, they're parity, sorry, I'm confused that they're parity non-invariant couplings on the branes.
That just means there's like branes and antidotes or something. This is a state in the theory, not a
Yeah, no, I know. So you'd say an anti-brane has the opposite parity.
something like that.
But then,
Is I important for you?
but then you're saying it has CP, but it doesn't have P because like you have to take the brane to the anti-brane to get the parity conjugate thing.
Yeah, I'm not sure. I'm happy to think about parity, but I don't. Yeah, I don't know. I haven't thought about the question of parity in this context, but I can think about we can discuss it maybe after.
Sure.
Yeah.
Maybe I is important.
Is I important for you?
Oh, the I here is because I'm writing the Euclidean, the Euclidean action. So.
Can you say again why flat space is not a problem? Wasn't the whole argument that in de Sitter you have an extra horizon, a cosmological horizon that you don't have in flat space?
Yes.
So now why doing the computation in flat space is logically correct?
Yeah. So what I'm saying is that you have two horizons with a distance between them that is 1 over Hubble. Okay, so as long as the process happens locally, so then it's approximately flat space. So the rate will be, you can do it in the more one can also do it in the full thing, but the
You mean the result won't change?
the parametrics will stay the same, and this is conceptually easier. So
Thank you.
Okay. All right. Okay. So then we can nucleate these branes, and then R is is a typical size of the configuration, and this is the field strength on the brane. Okay, so then so once we have that Euclidean solution, we can ask what's the action, and then the action looks like this. So there's a term from the tension, and then there's a term from the remaining two here. So this one and this one end up being the same order after you solve the equations of motion for FBR, and they give you something that with this dependence, and there's an order 1 number here that can be calculated numerically. And so you can extremize SE, which gives you the critical radius for these, the critical size of these bubbles, and it's set by the tension, alpha, and Planck and Havel.
So E is the background, is the bulk electric field.
Yes, E is the electric field. Okay, yes, sorry, and here, this is actually alpha E, but then I put E to be M Planck Havel. Okay,
So what is the meaning of extremizing S with respect to R? What exactly are you doing?
yeah, so we're picking the size of the of the nucleated bubble so that the action is an extremum, so it's a saddle.
You mean your previous thing did not solve the equation of motion?
No, it did. So we solved the equation of motion for F on here. And then so there's an ansatz for the profile, and then you put it so we can plug in the ansatz in the action, and then find the critical radius at which the action is an extremum.
But doesn't it grow? Isn't it a dynamical process? The brane nucleates a very small radius and then grows?
Yeah, so this is all done in Euclidean signature. So in Euclidean signature, so this is like the Coleman bubbles. So in Euclidean signature, we produce just a sphere, and then once you Wick rotate, then this will be a hyperbolically expanding solution. So in Euclidean signature is just like an S3 or.
You mean they don't grow?
In Euclidean signature, there's no time. So in Euclidean signature, they're like an S3, but then once you Wick rotate back, then they become expanding solutions. Okay. Any other? All right. Okay. So we can so extremize this, and then we find the critical radius, and then you can plug everything back in here, and this will be the bounce action that shows up in the exponent of the nucleation rate. So the brane nucleation rate will be given by this exponent for Navier black holes. All right, and so just like in the particle case, if this is not exponentially suppressed, then you can potentially get a situation where you nucleate many branes and you screen the electric field very quickly. And so if you want to avoid that, then this exponent, then this process should be exponentially suppressed, which means that roughly T2 to the 5/2 should be greater than this number. Okay, so for this process to be exponentially suppressed, we require this. But there's one caveat, which is that it is possible that the critical radius is bigger than Hubble, so that there isn't, then you have to compute a different instanton. Okay, so if the actual bubble that's nucleated does not fit in here, then one has to look for a different instanton, and we don't know what that instanton would be at the moment. And so either this has to be true, or the bubble, or this instanton that we're using has a radius that's bigger than Hubble. The radius is bigger than Hubble because we know what the radius is, just translates into another condition on the tension. And so in general, the tension has to be bigger than the minimum of this one or this one. Okay. And we can do this in general dimensions and for general P branes, and the tension is bigger than the minimum of things like this.
Can you just walk me through again, the calculation of the exponential rate? Is it really reliable in the regime where the exponent is, where it's not a non-perturbative exponentially small effect?
So right, so I think it's the same story where you have to think about, so what happens, for example, if the electron were very light, then it would screen electric fields very easily. And so somehow, if you think about dialing the tension to lower and lower values, then the process will become faster and faster. It's true, at some point you don't trust the calculation anymore, but the process does become fast. So there might be a different calculation to do, but the process does become fast parametrically when the mass or tension of the object is of order the electric field. Other questions? Okay, so in general dimensions, we get this. And so let me comment on the, so if the branes we're talking about are D branes, then we know alpha, it's set by G string and the string scale. And right, so if for D branes, we know what these quantities are like, and this one is typically smaller than this one. So because M string is bigger than Hubble, and so we're gonna get that this number is smaller than this. And and D branes actually saturate this, but they saturate this one. So D branes have a tension that is set by this number, and this is just smaller. So D branes satisfy this inequality. And this is a non-trivial check. We didn't do anything that says that use D branes except plug in the value for alpha at the end. Okay, so D branes saturate this part of the inequality. Okay. Okay, so that was the first inequality. So it's a lower bound on the tension of branes, and which we can phrase for branes that have a particular coupling. Next, we can consider a different kind of brane that couples to A wedge F rather than A wedge F brane. So here A and F are both, so A is the bulk field and F is its field strength in the bulk, and so nothing here lives on the surface of the brane. Axion domain walls couple like this. So axion domain walls have a coupling that looks like that. Okay. So I don't know of sources in brane theory that have this, but for an example could for instance be axion domain walls, but there's no reason why a fundamental brane cannot have this coupling either. At least, none that I don't know.
Weird, so A wedge F pull back to the brain. Directly.
Yes, it's A wedge F pulled back to the brane. Yeah, for instance, an example would be axion domain walls because they have a theta F wedge F. And then you integrate by parts, and then you integrate across the domain wall. So you get A wedge F on the domain wall. So it's like this. So I have a coupling of this. For example, we do 4D. And then you can integrate by parts and integrate across the domain wall. So they have a coupling that looks like A wedge F. Okay. So these branes, they get an electric charge whenever there's a background magnetic field. So the other branes, they could have a profile of F brane on them, and then they get an electric charge. These ones get an electric charge whenever there's a background magnetic field. And the charge of a little brane segment is proportional to the flux of the magnetic field through that brane segment. Okay, so for me to tell a story similar to the previous one, we need a magnetic field somehow. And but that's very easy to do because because the theory we're considering also has ionic black holes. So it has ionic black hole solutions which have both electric and magnetic fields. Okay, so the same theory we have has ionic Navier black hole solutions. So they're de Sitter 2 times S2, but they have electric and magnetic fields that stretch between the two horizons instead of just an electric field. And then we can go through the same song and dance. We can compute the nucleation rate for these branes, etc. And then you get the lower bound on the tension of the brane, which is like G M Planck H to the 3/2. Yes.
I didn't understand your argument for the A wedge F term. So I agree there's a coupling theta F wedge F.
Yeah.
If I integrate by parts, I get d theta times A wedge F.
Yeah.
The d theta is not adult defined field of brain.
Right, but then, so, yeah, you get this, wedge A, wedge F. And then, so this is, four directions, so I can choose coordinates where, one of the directions is orthogonal to the brane, and then the remaining ones are along the brane. And so I can perform, the integral that's orthogonal, so I can break up this integral into an integral that is orthogonal to the brane, times 3 integrals that are along the brane. Right, and so the integral that is along the brane, we can integrate that, and then d theta, for an axion domain wall, the integral of d theta through the wall is just 2 pi.
What are you doing at domain walls?
Yeah, for an axion domain wall, the integral of right, so for domain wall, if we do this integral, d theta will just get a 2 pi, and so this will have a coupling that's a wedge F. Sorry, also my indices now, yeah, but okay. Right, so this is the general. Okay, other questions? Okay, I'm almost done. I have one more slide. Okay, so we get a lower bound, but there's a loophole in this argument, which is that if there's a light axion in the theory that couples to the same F wedge F, then the axion can roll and screen the electric field. Okay, so the solution has an electric field that is screened, and I'll tell you, how that works. Because, like I said, the electric field in these cases is m Planck h, and is proportional to the electric charge, which is an order 1 number when normalized correctly for these black holes. But in the presence of an axion, there's the Witten effect, which means that the electric field is not just proportional to the electric charge, but also the magnetic charge of the black hole. Okay, if the axion is very light, we have to solve the equation of motion of the axion too. And the equation of motion of the axion will choose a value for theta that will ensure a very good cancellation between these two terms, because that's a lower energy configuration. Okay, so then the electric field can be parametrically smaller than m Planck h. And when the electric field is very small, there's nothing to screen, and if there's nothing to screen, then there is no argument. Okay, and so that's a loophole. So either the tension of these branes is bigger than g m Planck h, or there exists a light axion is the statement. Okay. This loophole is also the reason why we cannot apply this to axion domain walls. So this thing applies to these fundamental branes that have this coupling, but not to axion domain walls. And this would have been a very interesting bound for phenomenology, for example, and is actually the reason why we started thinking about this. Because if there's a bound like this, in string theory, axion masses, it's very easy to have exponentially suppressed axion masses. And what this is saying is that light axions put an upper bound on the cosmological constant in terms of an exponentially small number. So this goes in the direction of solving the cosmological constant problem. This also has very strong pheno implications. In particular, if we have high scale inflation, then we basically rule out all of the axion parameter space that is being looked for in experiments. Okay, but yeah, we could not prove this, and precisely because of this loophole. Okay, but this is, I think, a very interesting future direction to ask: is there a bound on the tension of axion domain walls, which would give a bound on the masses and decay constants of axions?
Why does it have something to do with cosmological constant problem?
Oh, because the axion mass can be exponentially small, and so this puts an upper bound on the cosmological constant in terms of an exponentially small number. So in other words, the statement would be large cosmological constant and very light axion is inconsistent. So if we have a light axion, then the cosmological constant is also small. And light axions are very natural. So light axions are. Yeah. But yes, but like I mentioned, this loophole actually prevents us from claiming that this inequality holds. And the reason is that in order to derive this inequality, we have to assume that the electric field is not screened, so it's m Planck h, But the assumption that the electric field is not screened already implies this, and so we don't learn anything new. Okay, I think I'm out of time. Okay, so let me summarize, well, I can summarize and then take questions. So I presented a bottom-up argument as to why the tension of branes in the sitter is bounded below. And this is a generalization of the Fastina-Lente bound. And there's a bunch of more things to work out. You can consider, branes that have different kinds of coupling to bulk gauge fields. You can consider, A1F or couplings to RR forms. You can consider different kinds of black holes that have a PMU charge, so axionic black holes, etc. So there's a whole list of things to do. It would be interesting to study also the pheno applications of these bounds. For example, if we can say something about, for instance, we might be able to link the string scale and the scale of inflation. Because the tension of these branes is ordered the string scale typically. So maybe there's a link to the scale of inflation and the string scale. And the last big question that remains open is there a similar bound for X on domain walls, which would be tremendously exciting in phenomenology. Okay, thank you all for your attention. Yes.
Any fantasy about what a top-down argument in string theory what shape it would take to give you this kind of bound?
From top down,
Yeah, can you
Well-
you just, fantasize about how this might occur in a fundamental theory?
right, so let's say we have some realization of like a metastable long-lived de Sitter. Then you have to ask what are all the branes that we can get. So for instance, you can write branes on various cycles, etc. And you have to ask what are all the branes that we can get, and then what are the tensions of all these branes. And then you can compare them to Hubble and then check.
I know,
I mean, in
that's
principle-
that's not a conceptual answer, that's just like, well, you check and see if it's true.
Yeah, I mean, I'm not sure if I have a better answer than that. Yeah, I don't know where it would come from. Again, it's just it's an IR argument, so I'm not sure where the UV origins would be. Of course, we believe string theory is consistent, so it should somehow satisfy this, but I don't know how it will end up happening.
I guess you could ask more generally if there's some top-down argument for cosmic censorship.
Right.
Since that's
Yeah.
driving the show,
Right.
whether to consider it or not.
Is it true that we never ever see a naked singularity from top-down constructions?
Yeah, I don't think we don't see. So if ever there are spacetimes that look super extremal from far away, so say you have a spacetime, there are these solutions, for instance, where a black hole can be spinning and it would look super extremal, but then if you look closely, then something happens. String theory would screen it, so there would be a different thing that happens before you can actually get to the naked singularity. So you would go to like a different dimension of space-time, or there would be branes or things like that that prevent us from.
But that might be an argument that in the low energy supergravity affected field theory, the naked singularity actually makes sense. It's just resolved by some UV data. Right?
Yeah,
That makes it sound like
Maybe
maybe not a
this is-
legitimate.
Yeah, maybe the scenario considered is
yeah.
okay, but in the end, even though in your theory you calculate that the charge goes down, but maybe actually something UV happens.
It's possible that, yes, exactly, it's possible, right.
Then the bound would not apply.
And then rest, but then cosmic censorship in general would not, but censorship is about whether you can actually see the singularity, so
No, but I mean, in the example you gave, you tune the parameters such that within the classical GR, it's a naked singularity. It's just that when you actually look close enough, there
see.
is some
There is-
brain, some extra dimension, something very UV that makes it
comes
so
up.
that it's
Yeah.
not actually a naked singularity.
yes, that could happen, for instance, yeah.
So in that case, this bound would not.
Yeah, in that case, there is no fascinality in general, I would say. Oh, yeah. Yeah. Somebody had.
I did, but it was going back to just a question that was in the very beginning. The reason why we weren't considering the other decay channels, like say photons or whatever for the black hole, that's just because we're considering very large, very cold black holes where Schwinger pair production is much more efficient than Hawking radiation, yeah?
Yeah, exactly.
Okay.
Yeah. That's-
But if you wanted the number, you'd probably have to, like a real number, not a squiggle in the bound, you'd probably have to take that into account.
Yeah.
Yeah, that's true.
You should also do, you need to also do a better calculation than just the exponential dominated.
Yes, exactly, that's correct.
Estimates, right?
Yeah, so there's a calculation, right, so one has to do the full thing, which is like, assume a full spectrum and then do the mode decomposition for everything and calculate every, yeah, there is a whole, right, that's why it's hard, so that's, nobody has done it. Yes,
When you were describing the nucleation of like the two brains, is that related to sort of like, should I think of that as like a Myers effect where you have like forming like a dielectric brain or something?
yeah, this is that part.
I have a question. So, in your case, are you imagining that the axion is light during inflation or heavy during inflation? Because if they are light, they just randomly fluctuate and you don't really get that screening factor. Right, you're not really, the axion is not rolling down to its minimum of the potential, it's just randomly fluctuating.
Right, so yeah, so I guess, so what we need to do for this argument is find a classical solution that looks like this, that has these two, it's the sitter 2 times S2 solution that has these two horizons and an electric and magnetic field. We're saying that the classical solution in that case does not have a large electric field.
No, but I think his question is more like, there theta is some constant, right? But this is a process that occurs locally somewhere in space-time. If the axion is light, theta is not taking its asymptotic value everywhere, right? There's
No,
a
but there isn't-
large quantum fluctuations of the axion.
Right, so I guess, yeah, if the axion is mass Hubble, then it would have large, but I think it doesn't need to be, I think it has to have, so the condition that the axion is too light is that MF is smaller than M blank H. So the mass can still not be Hubble. But yeah, the condition that the axion is too light is that MF is smaller than M blank H. And so the mass can be higher than Hubble, but then the axion can sit at the minimum.
Other questions? Let's take Julius.